Okay, so today we're going to continue talking about factorization and quadratic equations. Let me just remind you what we were doing last time. So last time what we were working with were things like this. Like, so we had an expression that involves x squared, and we wanted to factorize it. So factorize it means that you write it as a product of two linear factors. The trick that I told you you could do in this situation is that what you do is take the last number, like the one that's not multiplied by x, and you find how to break it into a product of two numbers. So -4, you could say that that's -1 times 4, or -4 is also 1 times -4. And also, for example, it would be 2 times -2. Okay, so those are like just a few ways in which you could break up um, the 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 number -4, and then you have to check of these options, which has a property that when you add them together, you get the number in the middle, right? So here you do -1 plus 4, you get 3. If you do 1 plus -4, you get -3, and if you do 2 plus -2, you get 0, right? So you can see here the third option is the one that works, right? Because that's the one that adds to -3 the numbers. So the factorization, you know, ends up being like the numbers end up being 1, -4. So it's x plus 1 times x minus 4. Okay. So that is how that is supposed to work. Let's see. But then, okay, so that is one option. But then there are like more complicated cases where it's not super clear what to do. So for example, let's see if I can. Okay, so here, um, if you have an expression like this, if you try to apply the same procedure, you have, like, I mean, the coefficient is -1, right? So you have to say, well, how many ways can you write -1 as a product of two things? Like, it's, well, at least in this case, like the obvious way to do it is like -1 equals 1 times -1. Like that kind of seems to be like the only good option. Okay. But if you just have like that, and you add them together, you get -1 plus 1, which is 0, right? So there doesn't seem to be like a really good way to make that one work. Right? So this is an example where like this method is not super useful. That's what I'm trying to say. So for like an expression like this, it's not that you cannot factorize it. Today, that's kind of what I'll tell you how to do. It's just that like this approach of like finding like the factors of like the last number is not the most convenient. So here, like the factorization approach that we did last time does not really work that well. We need to come up with a better way to factorize this. Yeah.
Think about quadratic formula.
Correct. Yeah, so that's what we're going to do today. But the key for doing that is that we need to talk about square roots. So that's what you need to do for that. So in order to tell you what to do in this case, we have to say a little bit about square roots. So a square root, I'll start kind of just as first with well, actually I'll start with like something kind of well defined for positive numbers. So for now, so n is a, a positive number, so, or let's say a negative number. So if n is a non-negative number, when you write the square root of n, so what is square root of n? Square root of n. This is going to be a number square equals n. So this is a number. So the easiest example, I mean, there are a couple of good examples here to have in mind. So quick example. So for example, if I have square root of 4, that just means I'm trying to find a number whose square equals 4. So like if you think a little bit about it, like you get 2, okay? So square root of 4 is 2 things. 2 squared, which is just 2 times 2 equals 4. So that is the square root of 4. Now, here's another one. Square root of 1 is actually 1, since 1 squared equals 1 times 1, which is 1. Here's another one, square root of 9 equals 3. For kind of similar reasons, since 3 squared equals 3 times 3, which is 9. One second. But now here comes like one that's actually kind of interesting. What if I say something like square root of 2? Right? So if I say square root of 2, well, you say, well, square root of 2 is square root of 2. It doesn't seem like very clear what you should put there, like being equal to. So, like, if I write something like square root of 2, it may not be super obvious. What should you put, like, what should that be equal to? Like, so what is this? Right? Okay, and then actually, like, the thing is that if you wanted to know what this is, like, you have to use Pythagoras theorem. So I'll tell you about what Pythagoras theorem says. So to find what this is, we need Pythagoras theorem. So what that says is that if you have a right triangle, so let's say you have a right triangle whose sides are called ABC. So this is a right triangle. With sides equal to, um, or called or labeled ABC, named ABC. So the only one, it doesn't really matter how you're calling them. The only one that really matters is that by C, I'm referring to what's called the hypotenuse. So the hypotenuse is just like the side that's opposite to the 90-degree angle. Okay, so whether this one is called A or B doesn't really matter. Like, but what I need to kind of fix for now is that if I write C, I do mean it to be the hypotenuse. So here C is just what's called the hypotenuse, which is this is the side opposite of the 90-degree angle, or like corresponding to the 90-degree angle. So like in a right triangle, two sides are always perpendicular, which are these two, and then the side that's opposite to it is called the hypotenuse. Okay. And so, you may have seen this before, but what Pythagoras theorem says is that, and this is kind of like one of the most important things in mathematics, is that the square of this number. So what does the theorem say? So I mean, this is probably one of like the oldest results of mathematics. Like the Egyptians knew it, the Babylonians knew it, the Greeks knew it, like everyone kind of knew it. Like it's kind of like one of the first things like that were figured out about numbers. So what like the theorem says is that like the square of the hypotenuse equals the square of one of the sides plus the square of the other side. So like to like what it kind of gives is like a relation, not between the lengths. It's not, it doesn't tell you that this length equals the sum of these two lengths, right? It's not what that is asserting. It's just saying that if you square this length, that equals the sum of the squares of the other two lengths of the triangle. Okay. And in fact, I mean, I kind of wrote in the notes why that's true. Although it might be kind of like a bit confusing to go over it right now, but it's not, it's like a very cute like argument, like you can, if you read it, like I think it would make sense on how I wrote it on the PDF, but at least I'll let you know that the way they thought about it is literally when I say square, they literally thought about it as a square, in the sense that if you have a right triangle. The idea is that if you had a right triangle, you can make three squares in this picture. So what are the squares? Like one square has side equal to A. The other square has sides equal to B. And the other square has sides equal to the hypotenuse. So it kind of looks like this. Let me write this a little bit above the picture. Sorry about that. So like the idea is that once you have a right triangle, you can make three squares like this. And what's the nice thing about these squares? What is the area of the pink square? Well, the area of the pink square is A squared, right? So this one has area A squared. This one has area B squared, and this one has area C squared. Let me color them. Make them more clear. So I mean, it may not be the way it was explained to you, but like before, if you have seen this earlier, but what Pythagoras theorem says is that the area of the yellow square equals the sum of the areas of the pink and the green squares. So it is like actually something referring to the areas of squares. So this is saying that like this area equals the sum of these two areas. And that's kind of like the best way to think about what it says. So it's like actually like a formula for areas. If you want, that is like the best way to understand this. So this is kind of like a result about areas. Which is not like, you do have to think about why this would work, because like, like if you have this green stuff with this pink stuff, why would you get the yellow stuff? Like, it's not super obvious. Like you do have to think about it. So it's not too bad, but it's like again, like if you're interested, you can read it on the PDF. You just have to make like two clever pictures. But the point is like you kind of think about it in terms of errors. Now, why is this related to the square root of 2 business? So let me go back to square root of 2. So what does this have to do with square root of 2? So Because if you do this, then what you can do is for example, draw a right triangle that also happens to be isosceles. Isosceles just means that two of the sides are the same. And we do like this. So okay, so let's say that you have two sides of a right triangle that are of unit length, right? Like this. Then what does Pythagoras theorem tell you about this right triangle? It says that the square of this side, right, equals the square of this side plus the square of this side, right? Someone's familiar with that? But what is it? It's okay, C squared is just like whatever that is, like I don't know what that is, but what is one squared plus one squared? That's one plus one. Right, and so you can end up finding, like interesting enough, you end up finding that C squared equals 2. So whatever this length is, it is a length whose square gives you 2, right? And that is precisely what we referred to as a square root of 2, right, before. Square root of 2 is like a number or a length whose square gives you 2, and that is precisely what you get here. So what I'm trying to say is that this is exactly, this is precisely. So what I'm trying to say is that if someone asks you what is square root of 2, like the answer you should give them is you draw a right triangle whose two of the sides are 1 and 1, and the hypotenuse is square root of 2. Yeah.
You just leave it as a square root of 2. You're gonna,
I mean,
if you know this, would you still leave it?
well, you would leave it as a right, yes and no, like it depends on what, yes, like there's nothing else you can simplify it to, like that is correct. But that doesn't like, make it clear why would there be a number whose square is 2, if you know what I mean. Like, you can, like, I mean, you could just like assert whatever you want, like, you could say, well, let me say, I'll call this like, like. Let me. Like I could say, well, cloud of 2 is like a number whose cube equals 2 plus 3 or whatever. Like, you could just start like naming proper like numbers with properties without even knowing where there are such numbers. So like, it is true that in practice, yes, in practice, if you see square root of 2, you have to leave it as that is. I mean, of course, like if you plug it into a calculator, it can be approximated. So that you were to write it on a calculator, it's not to make it sound like it's super esoteric. Like it's like 1.412, blah 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 blah. It actually goes for eternity. But yes, in in practice, you would leave it like it's okay to leave it as it is, but that doesn't like you do have to know that there is a reason why there's a square root of 2, and like that, if you ask for it in terms of a length, that's how you would find it. So like what I'm trying to say is that, if you think about it in the on the number line, where this is 0 and here's 1, if you were to locate like square root of 2 in the number line, what literally you can do is like kind of copy paste this segment here, right? And then there it is where square root of 2 is, which in practice, yes, like that doesn't like kind of allow you to simplify it in terms of anything else, but it allows you at least to locate it somewhere on the number line, if that makes sense. Without this, like you wouldn't know to begin with whether this could be done, like, you know what I mean? Like in the sense like there being like a square root of 2. That's kind of useful because, now that we will get, maybe just to make it more clear, like, why this is important, because like someone could write, for example, square root of -1, right? So you could say, well, square root of -1 should be a number whose square equals -1, right? And then you could say, well, that definitely cannot exist, right? But that actually is called like an imaginary number. Like it can be, you can make sense out of it, but it's a little bit more complicated, and we won't cover that in this course. But I'm just saying, like, just because someone writes this, like doesn't make it clear whether, there would be such a thing. So you do have to like kind of have like a reason for why square root of two like exists, for example. Otherwise, you can just start writing a bunch of weird stuff and you don't even know whether there's something with that property. So I'm just saying, like, square roots, like, my point is that the reason why there are square roots in general is because of like the Pythagoras theorem. Otherwise, you wouldn't really have a good way to like find them. Like, that's what I'm trying to get at. But yeah, like in practice, like if there's like a problem, I wouldn't expect you to simplify, any further what square root of two is, if that makes sense. Here's another one, like just to kind of like, did I answer your question? Like, here's another one, like, for example, like, this is kind of where, like, not that we're going to get into this, but like, that's kind of like, you would think about it in general, like, if now you make another right triangle, one of the sides is one, the other side is square root of two, because now you know that that one does exist. And so what does this one give you? So this one would give you, by Pythagoras theorem, c squared would be 1 squared plus root of 2 squared. So you get c squared equals 1 plus root of 2 squared is 2, right? Because of what we have been saying. So you can end up c squared equals 3. And that is what you would like to go root of 3, right? So like to find root of 3, which again, like this is also one of the others that you would not simplify any further, right? Like root of 3 is just root of 3 in a sense. But if you wanted to actually find like how it looks like, like the segment, like if you were playing with actual like pieces of strings, like, and you wanted to kind of like find the length of it, you would do like a right triangle of this sort and use Pythagoras theorem again to find them. Of course, like it's not that we're going to start finding like the square roots or anything like that in this way, but it's kind of just to show you, that that's how, if you wanted to kind of, if you want to like, this is kind of like in architecture, right? If you're designing like building or whatever, you want to know like certain lengths. This is something like that would come up frequently because that is like a good way to think about like how to find the lengths of those numbers. Okay. Okay, but that is kind of like just it was a small detour to say that that is how you think about square roots. And that after that, like I can't believe how to solve the quadratic equation in general. So let me see. Let me raise here. So why did I start talking about this? Because I wanted to kind of solve quadratic equations. So again, okay, so I want to kind of tell you a way to solve an equation like this. So we want to solve something like this. X squared plus bx plus c equals 0. Okay. So here are some examples of like the types of equations I'm trying to solve. So here are examples, like it could be x squared plus 3x plus 4 equals 0, or x squared minus 3x plus 4 equals 0, or x squared plus 9x plus 5 equals 0, or x squared minus 9x plus 10 equals 0. I mean, there are a bunch of different like options you could like write down. Like, so just imagine like I'm trying to solve any of these equations. Okay. So I'm going to give you a method which is different than the one that I discussed last time, where you would try to factor it. So the one I'm about to explain works in every single instance. That's the advantage that it has. It never fails, and it's kind of very clever. But for that, we did need to think about square roots. So let me try to explain how this works, and what it uses is something called completing the square. So what we're going to do is to complete the square. So we're going to solve this by completing the square. Let me just check which words I use. Okay. So first, what do I mean by that? I mean, if you think about the equation, I will kind of focus on the first two terms. So to focus on them, I'll rewrite. Let me just rewrite the equation a little bit by subtracting c on both sides of the equation. So kind of so I'll kind of I want the stuff with x to be on the left hand side. So I'll put it like this way to make it more clear. So like this is the focus of my attention for now. And now how this is like a very clever idea, but the point is how can I think of x squared? This is the x times x. So it's a product of a number with itself. Again, I can think about it as the area of a square. That's the point of multiplication, that if you want, you can think about it in terms of area. So what I'll make is like a tiny square. I'll make a square of size of length x. Okay. So if the sides are all x, this square has area x squared. Okay. And then how can I think about the other one, b times x? I can think this is the product of the numbers, so I can think about it in terms of a rectangle where the sides are now b and x. So let me put it like this. So this rectangle has area. Well, on the left hand side, I have a square of area x squared and a rectangle of area b times x. Okay. So far so good with me. Now, completing the square literally means what it says. Like it literally refers to completing a square. So just imagine like you had like if we had like scissors and like a bunch of paper to play with. What I literally would try to do right now is like cut this in half. So cut it in half. So just imagine cutting this in half. Okay, I'll write this all in green just to make my life easier. So if I cut this in half, like now the base is half the size. Okay, so like again, like, think about these two rectangles coming just from the bigger rectangle here. And then again, you could give this to a child, like you have like all these like the geometric figures, and then you kind of ask them to place them together. So I'll kind of put this one next to this one, right? To make it fit. And what I'll do with this side is rotate it and then align it here. Okay. So let's see if that makes sense. So I'll just copy paste. I'll copy paste the pink one. I'll just kind of keep, if I keep writing the letters like this will kind of look a little bit messy. So I'll kind of attach this first rectangle to this side, if that's making sense. I'll put it here. So let's call this like, just to make it more obvious, this is rectangle one, right? I have rectangle one here. I have rectangle two here. I have rectangle three here. So here's rectangle two, right? And for rectangle three, like I could align it here, but that's not super useful. So what I'll do is kind of rotate it so that I can bring it to this side of the square. So everyone. And you, okay, if you display it this way, you see, okay, there's some piece missing here. Like that's what completing the square means. Like you want to fill this out to get a square. So like you have, like you want to add like an extra piece that will complete the square. That's how like, that is what this means. So. Let me put it, like, I'll put it the. Well, I'll kind of put in yellow the square that I'm adding to this to come to get like a plain color effect. Okay, so now by adding this piece, I have a square, but you cannot add things for free. So if you add it, you have to subtract it for it to kind of still be the same in terms of like areas. So. So what this is asserting is like that the area that I have here, right, is the same as the area that I have with the completed square minus the area that I had to kind of add to fill out the gap. If that, is that making sense, kind of like in terms of like the areas and.
Like substitute.
Huh?
Substitute.
No, it's just kind of like, I'm just saying like, like think about it in terms of areas. I'm just saying like the area that I have here with these two rectangles is the same as the area that I would have in the completed square. But the price to pay is that you have to remove like that area just for it to kind of stay the same, right? This doesn't seem super odd, like, it doesn't seem at this moment why is that useful, right? But I'm about to explain to you why this is actually like a very useful thing to do. Because let's think about what this says, on this side. Like, what was the area here? Like the area here was like x squared. Right, like the area here was an area of the pink square plus like the area of the rectangles. The area of the rectangles was p times x. Okay. Okay, now this is a square, right? Like that's what I have been trying to tell you. Can anyone tell me what is the side of this square? Anyone wants to take a guess? Oh. Perfect, yeah, so this is x plus b over 2. Okay, so this, like the area of the big square should be x plus b over 2 squared. And what are the size of this yellow square? Well, if you look at the size of this yellow square, they're also b over 2, like, because all of this is b over 2. Here's b over 2. Here's b over 2. This is b over 2, and then b over 2. So this yellow square also has size equal to b over 2. So what is this area of this square? It's b over 2 squared. Okay.
What formula is this called?
It's called completing the square. So let me write it here. So what completing the square says. Let me put it like kind of like on its own, like without color, so that it kind of looks just like a single thing. So completing the square, what it says is. That x squared plus bx equals x plus b over 2 squared. Minus, well, what is this square? That's b squared over 4, right? If you want to kind of like simplify it a little bit more. So this is what completing the square says. This is like the key formula, like you'll see it will solve automatically anything that you could ever wish to solve about quadratic equations. Like this is like the key formula for everything.
It's exactly the same as the quadratic formula that we learned.
If we're like 3 minutes away from the quadratic formula, I just have to replace this into here, and then you will find the quadratic formula basically. So yeah, like just to go back to the equation which I was trying to solve. So let's go back to the equation that we were solving. So back to x squared plus bx plus b equals 0. Well, what I said is that you could rewrite it as x squared plus bx equals negative c. And then because of the completing the squares, right? Because of this magic formula. What is x squared plus bx? X squared plus bx is this. So that is what the left hand side becomes. Okay. So like that allows me to replace the left hand side with this formula. And then the advantage of this will become clear in like 2 seconds, but like the advantage of this is that you only see x appear once in this equation, whereas here it appears twice, like as x squared and b times x. So it kind of like allows you to rewrite things so that x only appears one time. And now I kind of want to solve for the quadratic factor, so I kind of add both b squared over 4 to both sides of the equation.
Wait, why is it negative 4 squared?
Oh, because the idea was like you have to go back to this picture. This was x squared plus bx corresponds to the area of these things, right? So what the formula says is that this area is the same as the area of what you get by completing the square. But if you complete the square, you have to kind of take it back, if that makes sense. It's just like the thing that you added, like think about it as a mini square tile, kind of like, you know, you have like, you're like putting tiles on like a room, and you had to add like a tiny tile to complete the tiling of your room. And so this area just happens to be b squared over 4, you know. And so what's the advantage of doing this? Well, the advantage of doing this is that you kind of I want to solve for like the square part, so I'll add just b squared over 4 to both sides of the equation. Okay. So like this becomes 0, so you get x plus b over 2 squared equals and like it's standard to rewrite this so that the square part appears first in the formula. Okay, so what is this? This is a number. This is a number whose square is this, right? This is a number whose square is this. So this number must be the square root of whatever you have on the right hand side. So what this is saying is that x plus b over 2 equals the square root of b squared over 4 minus c. That's clear. This is like a tricky part, but because like what this don't like it looks confusing, but like just ignore the fact that there's something complicated inside the square. It's just saying this is a number whose square equals whatever this is. So that is precisely what you mean by a square root. A square root is precisely something whose square gives you like a number. So that is why this ends up being like a square root. And that essentially gives you the value for x, because like then you subtract but b over 2 on both sides of the equation. And then that's one of the values for x. So there's something else I still have to say, but it's just making sense. And I'll do it in a few examples so that, you know, to make it a little bit more concrete. But are there any questions about this? So the other option, which I still haven't written, is that this could be the square, this could be the square root or minus the square root, because a square root or minus the square root both square to the same number. So for example, just to kind of clarify what I mean, you know, you could say, you know, I told you earlier that the square root of 2, that the square root of 4 equals 2 because 2 squared equals 4, but it's also true that negative 2 squared equals 4. You know, so whenever you find a square root and you multiply it by -1, that's also like a square root. because it's something whose square equals the same number. So the other option, like one option is for this to be kind of like the square root, but the other option would be for x to be minus the square root of that. Because like, if you have seen this before, like with a quadratic equation, you have two solutions. And that is where the other solution comes from, because if you have a number like, like maybe I should make it more like, make it more concrete, like, what I'm trying to say is that if you have something like x squared equals 4, what I'm saying is that x could be 2, which is the square root of 4, but also x could be like -2, because like a -2 is also something whose square would give you 4. So that's where the two solutions come from, like which are common from the quadratic equation. So, and that is precisely what solves, this solves basically any quadratic equation that you could ever want to solve. Well, I'm doing it here with the case, I'll kind of go back to it in a second. I'm doing it here with the case where like the coefficient in front of x squared is 1, but that's essentially all that you need, because after, like, if the coefficient is not 1, you can just divide by that coefficient, and you can always set it up. If that coefficient is 1. So like this is kind of like the basics of how to solve any quadratic equation we were ever. It will be the same as that, but in that case, like a equals 1. And you just have to reexpress this a little bit. So for example, like, so maybe just to comment on that, like, there is like another way you may have in this formula. But for that, you kind of like do a common denominator here. So you write this as b squared minus 4c over 4. And then this gives you, like, this 4 in the denominator can come out of the square root as a 2. So that's how, oops. Maybe I should, let me not kind of skip any steps. So another way which is written is, you rewrite it as b squared minus 4c over 4, right? But this 4 in the denominator can come out of the square root as a 2. And then you can just combine them together. That's
Where
right.
did the plus or minus come from?
Oh, no, the minus comes from here, sorry about, like, if you did this, you can do exactly the same for the other one, the only difference is that this one we have a minus, and this where the plus minus comes from. So it's kind of like the same formula as like the usual quadratic formula, if someone has seen it before, it's just, like in the usual quadratic formula is 4ac, it's just that my a is 1 for now, and then that's why you see a 2 instead of 2a, but it's exactly the same as the quadratic formula. The thing is, to solve the quadratic equation, I'll always kind of complete the square, and once you complete the square, you don't have to memorize the quadratic formula. That's basically, you'll see like in a moment when I do some examples. Does that make sense? So, but yeah, like this really solves every single quadratic equation in the world. So that is like the most general thing that you could do. So I will do some examples after the questions. So let me not erase this, because like this is like the key for making all of this work. So I kind of like will do it in practice. Show you how to make this work with some examples. So let's say you wanted to solve. Maybe this is my first one and I got. X squared plus 4x. So I'm always going to do it like, by completing the square root. Just because completing the square is like a useful thing that we will use tomorrow, so that's kind of why I wanted to emphasize this today. Of course, like another alternative is just like you use this formula right away, and then that's good, that's fair. I'm not saying you cannot do that, but it's kind of useful to see it like from the square, completing the square perspective. Okay, so if I wanted to do it completing the square, what I would do is, I would kind of isolate the stuff with x on the left, put it on the left hand side of the equations, which means that I don't want to keep this one here, so I will do x squared plus 4x plus 1 minus 1 plus 3. 1. So you get x squared plus 4x equals -1. Okay. And then this is precisely already in the same format as this one, like just that b happens to be 4, right? So if you could, I will erase this throughout the class because like then, like for all the problems we'll do today, that this will be kind of like the reference equation. So b equals 4 here, which means that b over 2 is 2, right? So like the completing the square formula says that, what does x squared plus 4x become? X squared plus 4x becomes x plus b over 2. B over 2 is 2, so x plus 2 squared minus b squared over 4. So b squared over 4 would be b squared is 16, so 16 over 4. So just to plug that back into the equation, like then you would end up getting like, so when you go back to the equation we had, this becomes x plus 2 squared. 16 over 4 is 4. So this is what you get from completing the square root again. And then you add 4 to both sides of the equation. So you get x plus 2 squared equals 3. Okay. Any questions up to this point? Oh, it's not there. I have to look at it because they're in there. Okay, and then again, what does this mean? This means here's a number whose square equals 3. So that number must be the square root of 3. That is precisely what square root of 3 means. So that's how you get the x plus 2 has to be square root of 3. Or what I was saying is that in general, that is the square, like, if the square of the number equals something, like then the solutions are the square root or minus the square root. So the other option that pops out is like x plus 2 could be minus the square root of 3. So those are the only two possibilities for like the square to give you 3. And so that's how you end up getting that x equal, like if you subtract -2 on both sides, you get -2 plus root of 3, or x equals -2 minus root of 3. Anyways. And those would be the two to that equations.
You would use this whenever you cannot figure figure it out using the other method, right?
Correct, yeah.
And it'll always be right.
This will always work, even for any of the older method ones, will work with this one. So this is completely general, completely universal, like it works in every single circumstance. Like the only thing that, sometimes it's kind of like get more annoying. It's like, yeah, you do have kind of to remember like the completing the square formula, or you would remember like the solution for the general quadratic equation like upfront, right? Like so like those are the two possibilities. The only reason why I'm kind of insistent on like completing the square is because tomorrow when we'll talk about more like parabolas and other things, and for that it is useful to think about it in terms of completing the square. So like that's the only like reason why I'm kind of writing in this way. If not, like the alternative that you end up with, or what like you could memorize, like is like if you have something like this, then x is minus b plus or minus root of b squared minus 4c over over 2. Like that is kind of what comes like what you end up getting from like this thing of completing the square. Which this is totally fine. It's just that again, it doesn't make much of a difference today, but tomorrow, this will looking at it from this angle is a little bit more convenient than just like straight up memorizing this formula. So that's kind of just why I'm kind of like insisting a little bit with that today. So let me do another example where there's not this number, it's not one, to show you that it really doesn't matter. You can always make it one like division. So okay, I'm gonna right here. And then I'll let you, I'm gonna have to redo the quiz, I'll let you work on some of these. Okay. So the first thing I'll do is isolate the axis stuff on the left hand side. So I want everything with the x on the left hand side. So I'll kind of add one to both sides of the equation. So you get 2x squared minus 3x equals 1. Okay, and then the next step is that all the formulas the way I have been writing them, it starts with x squared, like just 1 times x squared. It doesn't start with any other number. That can be easily fixed by multiplying by, in this particular case, 1/2 on both sides of the equation to make this coefficient 1. And this is actually a good excuse to remind you that if you multiply both sides by 1/2, then that affects both terms in the equation, like which is the same as dividing everything by 2, if you want to think about it in that way. So this gives you, when you do this, you get 1/2 times 2 gives you 1, so you get x squared minus 3/2 times x equals 1/2. Let me rewrite this here, like, so that it's a little bit more easy to read. And now this is ready to go because now you can compare this directly with this formula, the completing the squares formula, where b just happens to be -3/2 in this case. So b is always the coefficient in front of x. It can be positive or negative, that's totally fine. The formula kind of works regardless. So b is just like the number in front of x, which in this case happens to be -3/2. So if you use a completing the square formula. Oh, well, if b is that, look, we can work it out here. Like, what is b over 2? That's -3/4, right? -3/4. And what is b squared? B squared is just, I mean, the square like doesn't care about this negative sign, so you just get 9/4.
Wait, when you did the times 1/2,
Mhm.
on the other side, was it just to get like the x alone?
To get not the x alone, but to get the x squared, we multiply by 1.
Okay, so you just,
Right. Well, because in this case, like the coefficient happened to be a 2. If it had been like a 5, I would have done 1/5. And so you always do like the reciprocal of like whatever number you had in front of x squared, if that makes sense. And so if you plug that back into the formula, you get x plus b over 2. So b plus b over 2. B over 2 is -3/2 in this case. Square minus b squared over 4. B squared over 4, okay, b squared is this, so you get 9/16. Because like this is just b squared, and then you have to divide that by 4, so you get like the denominator becomes 16. Okay, and that has to be equal to 1/2. So you get here x minus 3/2 squared equals 9/16 plus 1/2. And it's kind of convenient maybe to simplify this a little bit further, like so. Let me do all the steps. And this is so 9 plus 8 is 17, so you get 17/16. So this is again like similar as before. This is the number whose square is 17/16. So whatever this is the square root of that number. So x minus 3/2 equals the root of 17/16, or minus the root of 17/16. I'm sorry, yeah.
How'd you get 9/16?
Oh, okay. You mean this one? So the thing is, like in the formula, you subtract the square of b divided by 4, right? The square b squared is 9/4, right? So you have to divide that by 4 on both sides, right? So kind of like if b squared is this, like b squared over 4, it's like what you get by dividing this by 4, and that's how the 16. Is that making sense? Where does
Think so,
the 16 come from? But no, thanks for checking that. Yeah. That's like the idea in this particular. Oh, sorry.
And you just turn the half into 8/16, just to have the same denominator.
Correct, yeah, so that it looks a little bit nicer. I mean, strictly speaking, I guess like you could leave it like that, it just like it looks a bit messier, so. And once you get to this point, like you just add 3/2 to both sides and then you have solved completely the problem. But you can see maybe from this, now that I have some examples, why it's kind of also nice to, when possible, to factor like, to solve the equations like we were doing like on Monday, because you are able to find the product of the two factors that add up to the middle coefficient, it is a little bit faster than trying to go through all this process. So there's like an advantage to the other method that we did on Monday, despite the fact that it is not as general as this. So here, it doesn't really matter what you, like, kind of which numbers you put into the equation. If it can be solved, it can be solved using this method, okay? Yeah.
So you say that we should learn to be the square over the quadratic formula. But what, like,
No, so what I'm saying is that, like, for tomorrow, knowing how to complete the square will be useful. So for just solving the equation, there's not much of a difference between both methods, right? So like either kind of works as well. The thing is like for tomorrow, like, so yeah, like if you're just trying to solve the equation, it's completely up to you which one you would prefer to use. The thing is like tomorrow we'll do things like this, like I'll just to give you like a heads up. So tomorrow I'll write something like this where I'm like, oh, let's find the graph of this equation, like which is going to be a parabola. It is a lot easier, to find this graph if you complete the squares first. And for that, since it is an equation that's not being set equal to 0, you cannot really use this formula, if you know what I mean. So like if it's being set equal to 0, then yeah, like you can totally do whatever you prefer. It's just that when it comes to graphing stuff, which is what I'll do tomorrow, kind of like this still works. But like, this formula doesn't really make a lot of sense anymore because like it's no longer set equal to 0, if that makes sense. So it's just for tomorrow's purposes that I'm trying to kind of like insist on this so that it looks a little bit more familiar. But yeah, if you're just trying to set, find the solutions to the equations, then yeah, you're free to use whichever. But there is some advantage just to getting used to this a little bit before tomorrow's class. But my philosophy is kind of like, yeah, as long as the method works all the time, I don't care which method you use, you know what I mean? But for tomorrow, it will be advantageous to see like, when we complete the square tomorrow, it will be super easy to see what's going on. But here, like, you're kind of stuck because this no longer will be 0, if that makes sense. Okay. Okay, so this is kind of what I wanted to say for, I'll leave this on the board because after the quiz, the problems